All right, hopefully this works out. All right, I think we can start. So, hello everyone. Today we'll be going over decision trees. Decision trees should be a lot more simple than the previous things we've gone over that all require the neural networks, and we'll get into the concept of interpretability as well, which is kind of the ability to understand why these networks or models do what they do. So, before we actually get into decision trees, I'm told that we will need to be going over more money donations. I know we've spammed you everyone a lot, but again, small donations from club members actually go a long way with Spring Give. So there's a bunch of different challenges that go throughout the Spring Give competition where if we get enough donations, we can win a much bigger reward. So one example they have here is let's say we get 4 people to donate the minimum amount, let's say it's $5. We could potentially win $1,000 just because we have like the most unique number of student donations within a given amount of time. I don't know if you guys heard about it in the Discord, but we're able to do something like this a bit earlier in the week where I think we raised $250 on our own. That got matched, so I got $500, and then because we won one of these challenges, we got additional $1,500. And I think this is like a great way where we get like the multiplier on our donations. Is pretty big. And again, all the money that comes in through here goes back into the club. So those prizes that we have for all the competitions, because of all this money that we're getting in, those prizes will be a lot bigger. So hey, maybe your $5 donation helps later on to turn it into, if you win a competition, maybe an extra $500,000 extra straight into just because you donated that extra $5. Not guaranteeing that you'll get the money back for winning the tournament or winning the competition, but this does help the club a lot by these small, $5 donations during this period of time. Hopefully this will be the last time we do have to shell out to everyone, but again, these donations do help. So let's get into it. So we'll talk about first the concept of interpretability, the difference between being able to see a decision tree versus a black box. Then we'll pivot into most basic of all computer science concepts, the if-else statement, and why that's such a powerful tool when building these decision trees. I have random forest up here as part of the agenda. If we have time, I can go over that a bit, but that's one of those things where we probably talk about a bit afterward just because, I don't know, if we want to get out through the code and that might take a bit. All right, so first off, interpretability. The definition of interpretability is the ability for a human to understand the reasoning behind a decision. So we haven't really mentioned this a bit before, but in modern day AI, we have such complex models. Think ChatGPT, right? It is this huge connection between these different word pairs and really no one fully understands exactly why it spits out one answer to another. You might say, hey, it came up with that answer because the word following it made the most sense given all the previous information. But that's a really vague statement. You really don't know exactly why it chose to put the words, I don't know, I like dog, dog. Why would it put dog after the word like? You don't really fully understand it from that kind of black box model. So we'll go a bit into the different types of interpretability. So the most uninterpretable model is simply just a black box. I'm sure everyone's heard of a black box model before. That's essentially you put an input, you have no idea what happens, but then it spits something out, and that's your data at the end. So that's the most uninterpretable model. So think of most APIs, if you're not given any documentation, you just throw something in, that is essentially a black box, and you get something, and you have no idea why. Then still really not uninterpretable are neural networks. We talked about it, but every single neuron connects to every other neuron, and it's just this really huge web of connections. So we could say, hey, maybe certain of these neurons maybe have lit up due to the different training weights that we use. And therefore, it came out with the output that this object is probably a dog rather than a cat. Maybe it comes up like that. But again, we really don't know exactly what do each of these neurons mean just because this singular neuron was very important. So what, right? And so there is a lot of research currently going on to make these neural networks a lot more interpretable. But in part of this scale, it's really hard to understand why it came up with these decisions. The next thing is just a regression model. So as you can see here, it's pretty obvious why a model would come to a certain conclusion. So for instance, if you look at this, we have this model that is trying to identify whether a flower is a setosa or not a setosa. If you recognize this is from the iris data set from scikit-learn. But you have the two types of data, or two attributes of data, sepal width and sepal length. That's just part of the flower. And then we can see that the model had learned that, hey, if the sepal width and sepal length are greater than whatever this line is, which looks to be about maybe 2x plus 1. I don't know, that's something looks about right. That's how it's able to reason for whether or not it will predict that flower being a setosa or not a setosa. And so that's just something that is more interpretable than that neural network. So this makes a lot of sense, but we can go a step further. The if-else condition. So we'll get a bit into this about how the if-else condition relates to a decision tree. But essentially, this concept of having a condition and doing one thing if it's true and another thing if it's not is by definition the most interpretable thing because it's literally telling you why it's making that decision, right? The condition, if this image has an eyeball, it's probably a person, something like that. It's that statement in itself is the interpretable method as it says in almost human readable language what's happening and why it's making those decisions. So let's go into the if-else statement. A lot of this we'll go through is some college admissions, some very basic. So if you look at this, we're given if you have a good GPA, you'll be admitted to the school. If only that were the case. And if you don't have a good GPA, so that else statement, you'd be rejected. You know, everyone's seen the if else statement before. You've all coded before, I'm assuming. But this is very simple. And what if we can then turn this into our own model, where we have just a bunch of these if else statements that predict whatever we want to predict. So again, we have it now changed the format a bit into looking like a tree. Can I get a raise of hands of who here has done anything with trees in any of their classes? I'm assuming if you're CS related, this is going to be something that's going to be very familiar. All right, good. So just like regular trees, if it's false, we'll go down to the left. If it's true, we'll go down to the right. All right, so let's make this a little bit more advanced. Let's say instead of just a good GPA, if you have a good GPA, then you have to go see if you have a good SAT score. And if both of those are true, then you would get admitted to the school. If both are not, you would get rejected. Either good GPA or good SAT are not good, you get rejected. And we can keep complicating this even more. Keep adding these different nodes here, which are our decision nodes. They each have their own conditions. Maybe instead of, let's say you have a bad GPA, but have really good extracurriculars, you're also admitted. This again, now our tree is getting slowly bigger and bigger, and maybe becoming a bit more, having better prediction scores, right? Because now we are looking at if you are the leader of the basketball team, maybe now you don't have good GPA, you might still get admitted. And so this decision tree here, or this mini tree that makes decisions, kind of learns to get better and better. And we can again make it slightly bigger. So now if you not only do you have to have good extracurriculars, but you also have to be the MVP on your sports team and so on. And this will keep getting bigger. And we could see that this actually is a thing that is used and talked about in college admissions, using these decision trees to help look at who's being admitted to these schools. So this is not one thing to choose your what school you go to or get into a school. This is more for the analysis of it. So if you want in your free time, you can go look at this article here. It's a pretty nice paper on analyzing how we should improve our college admission process. Just a quick sneak peek. All right, so let's go back to the model we talked before. As we can see, this is a decision tree that is a lot bigger. Before, we're talking with decision trees that had a depth of 3, because notice how there are 3 conditions here. Technically, you can also consider this a depth of 4, because if we include these leaves, that would be a depth of 4. But these decision trees can get a lot bigger, such as this one with a depth of 6. So I guess that would include the leaves. So let's go back into this tree just to make sure everyone gets a general understanding of how this works. So looking at the person number 1, John. Can I get someone to tell me whether or not, according to this tree, we would predict him to get accepted or not accepted? And then also explain why. So I'll do the first one with you guys, and then I'll ask you again. So let's start off at the top with John. So first, does he have a good GPA? Let's look at our chart. First, it says he does have a good GPA. So now we check, does he have a good SAT? Well, it says that he does have a good SAT. And so that means we can keep on going to the right. The last part, it says, is he suspended? Was he ever suspended in school? In our case, no, he was not. So what should our acceptance be? Yes. Hopefully I put it down. Yes, I did put it down correctly. All right. Now, who wants to give it a shot for Joe? Is Joe getting admitted or accepted? Or admitted or rejected? Rejected. And why is that?
Bad GPA, so it goes to the left on street, and then the good SAT doesn't matter. Good extracurricular, but not an MVP.
I'm gonna take your word for it. Did I put that? Yes, that is rejected. So again, if you follow the tree along to get to an eventual leaf, which are those predictions, we can see that it's rejected. All right, who wants to take the last one? Yes.
Okay, rejected because good GPA and bad SAT immediately goes to rejected.
And one thing to note here is that even though he has a good GPA but bad SAT, he still gets rejected. As if you look, let's say he had a bad GPA, we could see that, hey, he does have good extracurriculars and he was the MVP. So if he did have a bad GPA, this tree would predict for him to be admitted. But because he does have a good GPA, it doesn't show it in that case. So there's a bunch of different things to think about in decision trees for that. So yeah, he is rejected. So now that we've looked at what a decision tree kind of looks like, how are we able to actually figure out and train our trees to come up with those nodes? And so we are going to be using the concept of information gain and entropy. There will be some math up ahead, but I don't expect you guys to memorize that. And it's more of just understanding the concept of randomness and trying to decrease the concept of that. So let's get into that. So entropy. Entropy is essentially just the measure of randomness. And one thing you can think about is pulling a bunch of red or blue balls from a box or a bag, right? So if we have 10 balls in total and all of them are red, if we pick one ball out, it's a guaranteed chance of getting a red ball, right? So that means in that case, our entropy would be pretty much 0 because there's no randomness in that because you're guaranteed to get one blue ball. On the other hand, if we have one red ball and 9 blue balls, there's a little bit of randomness to it, right? But it's not a ton of it. You're basically, if you're just going to predict that it's always going to be a blue ball, you'd get it right 90% of the time. And so we can kind of see in this graph right here, the expected entropy for like the ratio of red to blue balls. So the greatest amount of entropy or the most amount of randomness would occur when there's equal amounts of red balls versus blue balls in the bag. Can I get thumbs up if that makes sense in terms of entropy? All right, next, so let's go on to that second example. Another one of those, the GPA. So if we look at, let me just go back to the single attribute GPA. So this single attribute entropy is the calculation that is the sum of the negative probability times the log base 2 of that probability. So let's look at that for the example of getting accepted into a school. So as you can see in this graph, there are 20 people, 11 got accepted, 9 got rejected. So how are we able to identify or estimate the entropy for this? Well, let's use this equation. So we're going to be summing over the rejected and the accepted groups. So let's first go over the rejected group. So if we use this equation, the probability that someone is rejected, 9 out of 20. Does that make sense? Well, so then we do negative 9 over 20 times the log base 2 of 9 over 20 plus, now we are going to go look at the probability that someone is accepted. Because again, we are going through both the rejected and accepted groups. So you can go look at that, and it's just this right part of the equation. And we get this pretty high entropy because entropy is going to be between 0 and 1. So as you can see here, if we have a total of 11 people are accepted, 9 people rejected, there's going to be a decent amount of randomness in here. Does that make sense? All right, let's go into that multi-attribute entropy. So in multi-attribute entropy, we're going to be looking at entropy with respect to something. So in this case, we're going to be looking at the probability that they were accepted with relationship to their GPA. All right, so let's look at that. So now we're going to go check out this equation here. Again, I don't expect anyone to memorize this. I'm just going to go over the math. Just understand the concept of being able to understand that entropy is randomness is really all you need to grasp here. So multi-attribute says, let's check the probability of a certain thing happening. So in our case, we're going to be talking about acceptance and GPA and their relationship to one another. So what is the probability that someone is with a GPA of 12, or what is the probability that someone exists with a good GPA? If you check on our graph here, that is 12 out of 20. So again, our probability of C is 12 out of 20. Now we want to multiply it by that entropy that we calculated before. So if you do all the math again, we get the entropy being 0.65. And the reason why it's 0.65, it's much lower, is because if we look at all the people who have good GPAs, it's a 10-to-1 ratio, which is a lot, which means that there's going to be a lot less randomness than there was originally with 11-to-9 ratio. So does everyone understand why that entropy is a lot lower than we had originally? I'm guessing a little bit nods. Okay, I'm losing each other. We'll get back to this in a bit. All right, and then same thing with a bad GPA. So when we look at the entropy with respect to the GPA, we could see that entropy is a lot lower again. So it's 1 in 7. Example of pulling red and blue balls out. It's going to be a lot lower of randomness. We combine that together, and now we have our multi-attribute entropy. So again, that's like the entropy of acceptance with respect to GPA, where our acceptance is our state and our attribute is the GPA. So that's about 0.61. So we can see how we're slowly starting to trim down the amount of randomness by selecting an attribute to look at. And so now we can go into information gain. So information gain is a key part of being able to change up or figure out how we should be splitting up our decision tree at each node. So information gain, simply put, is the measure of how well an attribute separates the samples by the class. And again, the class is that prediction that we're trying to make. So using that same example, we're trying to figure out how does looking at, for instance, the GPA affect the entropy of the entire situation. So I'm not going to go over this math again since we just looked at it, but essentially it's just the entropy of the starting, which we were just looking at was accepted versus rejected, minus the entropy of acceptance given their GPA. So we can just take the subtraction of it. We just did the math previously, and we got 0.38. So that means our information gain, or by looking at GPA, our entropy changed by 0.38. So we'll get into why we want to actually use an information gain in the next slide. So does everyone understand that section right there? Can I get a thumbs up, middle, down for how they understand the concept of entropy and its connection to information gain? All right, I'm seeing some thumbs up, some thumbs in the middle. Hopefully when we talk about how it breaks up a tree, we can get a better understanding of that. So let's go look at our college admittance tree again. So how are we able to build it? So the idea is we want to break up, or we want to create a node that does the best job at decreasing the amount of randomness, right? So again, let's say we had the bag of balls again, right? And now we have every single ball has a number on it and a color. And so we want to split that up into two separate bags that separate into a red and separate into a blue. We want to make sure that by pulling a ball out of the left bag, we get almost all red balls, and pulling out the right bag, we get almost all blue balls. And so we can maybe figure out a good number to separate the two bags into. So maybe it turns out almost all the red balls have a value of less than 10. So maybe we split it up into, if it's less, the value of the ball is less than 10, we put in the left bag. If the values of the balls are greater than 10, we put in the right bag, and that hopefully separates the two bags into mostly reds and mostly blues. So we do the same thing with the concept of college admission. So the first node we want to look at is which one of these do we think would probably do the best at separating our people based on acceptance versus rejected? Hypothetically, maybe the GPA is the best way of kind of separating it out. So out of our entire data set, turns out if you have a good GPA, you have a 90% chance of getting accepted. If you have a bad GPA, there's a 10% chance of getting accepted, something like that. And so because there is that huge change in, or being able to distribute the data into accepted and non-accepted, we want to be able to, again, have that concept of, or maximize the concept of information gain, which is that change in entropy. So we want to remove the randomness when we split the node. And so that's how we're able to identify how we should be splitting node. Again, when we go over the code, hopefully it should make a bit more sense. But if we look at here, again, once we split the node once, we can then choose another attribute to split the data on. So let's say, given that they have good GPA, what is the next best way of splitting them up such that we can put accepted in one side and rejected in the other? And in this case, we have good SAT. So it turns out if they have a good SAT, or given that they have a good GPA, the next best way is to split it up by SAT. And again, that concept of removing randomness from the data set by splitting it up into two pieces is how we can identify that threshold that we'll get into. So I guess the better slide is right here. So I probably should have gone over here. Did I see a hand raised up? Yeah.
Is there a difference, like statistics, between measuring correlation and measuring the entropy?
So the main point of entropy is that randomness. They are similar, but they do have like different definitions, with correlation it has to do with like expected value, the difference between expected value or it's like the expected value of the true value minus the expected value. I don't know. They're different in statistics. I don't want to go into all the math statistics, but just know that correlation probably looks at the difference between the data, whereas the entropy looks at the amount of randomness in a situation. I don't know if that's the best explanation for that. So I think I threw around the word threshold a little bit before, but previously all of our data was binary, right? And so we're able to just look at the different attributes and say, hey, if it's true, we'll split it there, right? True or false. But let's say we're given a integer or a floating point number, and now we have to figure out, how do we split it? And so we want to do now is use the concept of a threshold, where we now say, instead of the GPA being true or false, the GPA needs to be greater than a certain threshold. So that basically turns that integer, or the comparison of integer, into that Boolean condition. So if we see here, what is a good way of breaking up our GPA into admitted and rejected? Does someone want to give me a good threshold to use to kind of split up the data to be to decrease entropy or have the most information gain? Yes.
It's 3 or above. It's accepted, otherwise it's rejected.
3 or above. Yes. I mean, it's not a perfect method, because as we see here, 3.0 is accepted, but 3.2 is rejected, right? We're never going to get that perfect split, which is why we have the concept of that randomness. Instead of just being yes or no, it's going to be perfect split. And so, yeah, as we see here, if there's a, if we split it at 3.0 or greater, we have that true, the amount of people that are accepted in is 1, 2, 3, 4 out of a total of 5 data points. So the right side would be 4 out of 5 chance of being correct. And if we split on the left, so that means when the threshold, when it's less than a 3.0 GPA, which is their 2.9, 2.8, you'd be rejected, and that has a 2 out of 2 chance. So the entropy on the left would be perfect. Entropy on the right would be not perfect, but as close as we're going to get. And so we're trying to, again, minimize the entropy for the, minimize the entropy here. And we could do that using that concept of information gain. All right. Do we have any questions about the slides before we go into actually coding this all up? Yes.
Can you go back to the
Information gain or entropy?
this one? So
Right.
So it's saying information gain is the entropy of the tree minus the entropy of the tree in respect to X.
Yeah, essentially, it's like, what is the entropy of what we have currently, subtracted by the entropy of what we have if we like divided it up by a certain attribute. So remember we talked about how originally entropy of T, the T in our case is going to be the whether they got accepted or not accepted. That's broken up by 11,9, right? Which is, there's going to be a lot of randoms in that. Whereas if we looked at whether they're accepted or rejected with respect to their GPA, instead of it just being 11,9, now it's 10,2 and 1,7. And so therefore there's going to be that the entropy when we're talking about with respect to the attribute of the good GPA versus bad GPA splits up our data really well.
So is X always like a classifier or?
Yeah, I think I have here. So T, the current state, just think of that as the class, the prediction. And then X being the attribute that we're looking at currently. And so for this example, our selected attribute that we are taking the entropy with respect of is GPA, whereas the state or class is always going to be accepted or rejected.
And do we just compare like different attributes and say which information gain is the high information?
Yeah, we want high information gain. We want a high information gain because that just means there's a big change in entropy because we want to decrease entropy, and it's the difference of entropy before and entropy after. And we want the biggest change. Does that answer that question? I'll go a bit into comparing information gain in a second. Yeah.
Okay, so using the equation for multi-attribute entropy, we have an input C, but in this case, is C the what exactly is C here? Is it the accepted, rejected, or the good GPA bad?
So as we see in the summation, C is an element of X. In our case, X, the attribute, is our GPA, or GPA is the attribute. So as we are iterating through the attributes, C would start off at being a good GPA, or I guess in the case here, yeah, this would be good GPA. And then the second time we iterate through it would be the bad GPA.
Okay, so that's calculating the randomness of accepted and rejected within the good GPA category and the bad GPA category?
Yeah, essentially that.
Oh, okay.
So for instance, let's say we had more attributes rather than just good GPA versus bad GPA. Let's say it was, in addition to the GPA, shoe size, right? Obviously, if we try to choose whether or predict someone is going to be accepted by their shoe size, those things, I think someone mentioned about correlation, those probably aren't very correlated, right? Your shoe size probably has nothing to do with whether or not you'll get accepted or rejected from a college. So breaking it up into accepted or breaking up your acceptance rate based on your shoe size probably won't help decrease the amount of randomness, right? And so when we try to compare the information gain, given GPA or your shoe size, we would select to break up our data based on GPA just because it reduces that randomness.
Okay. Yeah, so we can think of this sort of like a weighted average of entropy given some new information.
That is one way to put it, yes. Essentially, just the main point is if you're doing with respect to attribute, you just break up the entropy by the chosen attribute. All this math stuff you don't need to memorize, just the concept of trying to decrease the amount of randomness by breaking up the data by some attribute given. Any last questions before we go on to yes?
The first parameter is always the attribute you're trying to predict.
Yes, yeah, it is. Yes.
For the multi-attribute, is it saying a higher number means the selected attribute is making it have less entropy, or is it a lower number saying the selected attribute is making it have?
So a higher entropy always means more randomness.
Okay.
So multi-attribute having a high entropy just still means more randomness.
Okay, so that's why you want the IG equation to be high, because that means the multi-attribute equation was low.
Yeah. So like the difference between entropy before and after we split up the data is a lot. There's a big change in entropy.
Isn't that, wouldn't you want, if you want a bigger change, wouldn't you want a number that's just very different from each group, or like lower?
Yeah, obviously you want to minimize, the goal is to minimize the entropy given the attribute, right? And so we're just trying to measure the change in entropy here, right? Because if we just say our score is the entropy, then there's not like an improvement, the concept of an improvement anymore.
Yeah, okay, I get it.
Yeah, it's just the simple concept of just measuring the change in entropy in this case. All right. Could I get I'll do a hands up for like your understanding of between 1 and 10. So if you're feeling, or if your confidence is between 1 and 3, I got a raise of hands. All right, that's good to see. 4 to 5 or 4 to 6, 4 to 6. I raise of hands if you understand this. It's okay. I just means I should probably cover more a little bit later. 7 to 10.
Can I just say 7?
Yeah, you could just say 7. Yeah, that works. All right, so I'm gonna go on the assumption that people mostly get it, which really is all I'm really trying to get. Just on the you can ignore the math, just entropy again, measurement of randomness, whereas information gain is that change in randomness or change in entropy. All right, let's go on to the code. So let's ignore the feedback form. We'll get to that later. Then we're gonna go to that first tiny URL, which should get us to the decision tree Colab notebook. So we're going to try something a bit different today. So there's going to be a couple lines missing in the Colab notebook. So if you follow along, you should be able to, figure out what goes there. If you want, you could try to go ahead and fill in the blank. You should be able to do it on your own, but probably nice to go through it together.
Is that possible?
I think everything's lowercase. For whatever reason, this font everything's always capitalized. Yeah, for some reason the feedback form font isn't. Maybe they're just using different fonts. Is everyone able to get to the Colab notebook? Yeah. All right. So again, you do have view only access to it. So if you want to edit it, you do have to create a copy of it to mess around with it, which I suggest everyone does. All right, I'm gonna go. Does anyone still need a link before I, get off this page? Still need a link? All right, I'll give it a bit. All right, I'm gonna assume everyone has the slides or the screen share was stopped. Okay. All right. So everyone sees something like this, right? Yeah, everyone sees their screen looks like this. Do you guys want me to zoom in actually?
Yeah, that is.
Keep zooming in, or is this good? This good? In the back? Looks good? All right, perfect. So we're first gonna, we're actually gonna be building a decision tree from scratch. So everything from actually coding up entropy and information gain, we're gonna do everything and just use NumPy as our source. So first thing we're gonna do is we're gonna import a couple things. Things at the top, NumPy. Hoping everyone's heard of NumPy. Pandas, that's just for the data collection. I don't even know if that's needed, but we'll talk about counter later, train test split, and the rest is just for visualization. So let's run that. And if you want, we can also look at the different data sets I've been using. So this one actually has 4 different data sets that you can play around with. That you can go look on your own, but those are just different data sets that we'll load in later. So we'll run that as well so we can get that for later on. All right. Now let's get on to entropy. We just talked a lot about entropy, so hopefully a lot of this makes sense. So the first, our entropy is going to take in a list of ones and zeros. So if you look at this test right here below, it's just a list of zeros and ones. And we want to get the count of how many zeros and how many ones are there. So that on that line on code on line 9, that essentially looks at our list and breaks it up. So it says, hey, right now there are 7 zeros and 3 ones. So the new array of counts would become 7, 3. That's just what line 9 does. Now we want to just get the probabilities of those. So instead of now we have 7 out of 10 and then 3 out of 10. Remember again, that's where because again, we want to get the probability of something times log of that probability. That's how we get entropy again. So let's set our base entropy to 0 and let's iterate through all of those probabilities. So does anyone know what we should be putting here? Because we want to make sure first off that the probability is greater than 0. But we want to increase entropy. So remember again, the equation we talked about before, but also here. Does everyone want to take a shot at what we should put in this area? So this is actually where we add up our entropy. Anyone take a shot? The hint is that it's literally right up here. Yeah.
Prop times log 2 prop. Technically, entropy.
Yeah. So we want to increment our probability, or my bad, not our probability. We want to increment our entropy. So because our entropy is incremented. What am I doing? Incremented by that probability. So prob times, and then we want to take the log of that probability. The log function, base 2, is just going to be np.log2. That's how we're just going to use our log function. np log 2 of prob. Oops, prob. So does everyone understand why we do this? You get thumbs up, thumbs down, thumbs middle. Everyone understand why we put that there? All right, nice. Let's see if this works. You run it, and our entropy gets 0.881. Hopefully everyone has something like that, right? Yeah, you have a question?
Is that returning negative entropy?
Yeah, we are returning a negative entropy. So the reason for this is, remember how before I said that the entropy is the sum of the negative probability times log base 2 of probability. We're just taking the negative sign outwards. I mean, technically, we could do minus equals It's a whole thing, but this was just a simplified way of it. Yeah. NumPy. That's just a package that we input.
Okay, so is that just taking the log base 2?
Yeah, that's just the log base 2 algorithm. Yes.
What exactly is bin count doing? I was trying to read the documentation. It didn't make a lot of sense.
So bin count essentially counts the numbers of zeros and ones in our list. So if we give it, again, for this list right here, this is 7 zeros and 3 ones. Bin count would return 7,3 because there are 7 zeros and 3 ones.
Oh.
Yeah, it's just a nice counter function for us to get the probabilities. It's pretty simple, right? You get it now? All right, nice. So let's move on to information gain. This right here is going to look a little bit foreign to everyone just because we looked at information gain a bit differently. But the main idea is that, again, we have the entropy that we start with minus the entropy or the probability of the data split up times the entropy of that split up data plus the probability of the other split times the entropy of that split. So in this case, we have left and right. That's the left child and the right child of the tree. Can I get a thumbs up if everyone recognizes this? It's just the concept of splitting up the data. All right, perfect. So let's get into here. This one's actually much shorter. So we're just quickly getting up our the probabilities of the left, probabilities of the right, which is right here, And what should we return? Who wants to give a shot at that? I saw your hand first.
They will use the entropy function we just
Yep.
made in the so entropy parent minus prob left. I mean parentheses prob left times entropy left plus prob right times entropy right.
Yes, correct. One thing to note, instead of just left and right, it's left child, right child. But yeah, that's exactly right. Hopefully I can type this correctly. Parent, and then it should be minus. Prob, we'll do left first. Left times the entropy of left child plus the probability of it being the right times the entropy of the right child. And again, our data is the parent, which is again just that list of all the data. And then it broken up into a left child and right child split here. That looks like I misspelled child. Does everyone have that? Or does that also make sense? Can I get a thumbs up, middle, down? It's just everyone's idea. How's it over there? Thumbs up, I see. Look, all right, sounds good. So we should be able to run it on our next one, and we should be able to get something that looks like this. Our information gain, or the change in entropy, is about 0.18. And if you look at that, it does make sense for us actually to have a positive information gain, because we start off, there's a lot of the mixture of ones to zeros. It's pretty mixed, but we were able to split it up a lot better with that left child versus right child here. The right child probably does have pretty bad entropy, so it has a pretty high entropy here, but the left child has much lower, so it evens out to be slightly lower than the original entropy. So that's where we have that positive information gain of 0.18. Yes?
I got 0.09.
0.09.
Don't know if that means if I made a typo or something, or if anyone else got 0.09.
Did anyone else get 0.09? 0.98.
I got 0.18.
Wait, did you put a plus instead of a minus? That could be just flip a sign.
Also, make sure the parentheses are correct, because again, it's minus, and then this whole thing is together. So
Or just expand my.
hopefully that works. All right. If anyone needs help, just raise your hand, and we can always come back to that. All right. So now we have both our entropy and information gain coded up. Those are pretty simple functions. Again, they're just following those math equations as we talked about earlier. All right. So now, how do we split up all of our data? And so we'll create another helper function that takes in a bunch of attributes, which is our x, and our classes, or the true classes, which is our y. So we want to figure out a specific feature or attribute. So that's when we talked about, should we split it based off of their GPA, their extracurriculars, their SAT? This is where we choose that. So the goal is to find the best place to split up our data. So you have to do two things. One, we have to figure out which attribute is the best to split, and also the threshold for that because we could be working with more than just Boolean data. We could be working with that integer data, which is again, we talked about threshold. So let's go through the data. I'm going to skip a bit of the stuff here, but we start off by just remembering what our perfect or best or maximum information gain so far. So we start off at -1. Let's just get the number of rows, numbers of columns, and let's go through every single column of our attribute list. And so now that we're at a specific attribute list, which is that first for loop, we can look at the second for loop, which then tries to test every single threshold to split at. And one of the things, again, AI or machine learning takes a long time to train. This is why. For every single time we want to figure out the best split, we have to split the data at every single possible threshold to split it at for every single attribute. So if any of you guys have taken CC 101 or know the concept of timing algorithms, this would be O(n) squared because it is that double for loop here, not including the whole concept. It does. It sucks a lot because the thing is, we're not just calling best split once. We're calling it for every single node of our decision tree. So there's a lot of better, faster ways of doing it, but this is just the easiest to understand. So we look through every single attribute, every single threshold, and then we split up our data right here. So notice how we split it. If our data is less than or equal to the threshold, that goes on the left. If it's greater than the threshold, that goes to the right. And then we call our I almost gave you the answer. All right, let's go to right here. Let's go calculate our information gain. Does everyone remember how to calculate information gain? Heck yeah! All right. So what exactly do you think we should put here? So looking at how we split up the data, so we put in it left and the right, and then we also make sure that we only have that one-dimensional left and right data, which is the classes. So using this right here, does anyone know what to put here for calculating information gain? They want to take a shot at this one, and then yes.
The X curve, X, Y, left, X, Y.
So as the parameters for information gain, I'm assuming you're talking about. Yes, it is. So you want to wait a second. X curve. What is? Oh, X curve is. So right now, X curve is just multi-dimensional. So when we give our data to information gain, we want to make sure to give it the class of our data, right? Rather than the attributes, because we split up the attributes. That's where it goes into left child and right child. So that's why we want all of our data to be the actual class. Does everyone know what I mean by class versus attribute?
No.
All right, great. I should probably start with that. So everyone understands the concept of input and output of a function, right?
Yes.
Attributes are essentially the inputs to the function. So if we talk about for acceptance, getting accepted to a college, whether or not you're accepted or not accepted, that is the class. Sorry about that. That's the class or the prediction of our model. The attribute is all the other data that we give it. Their GPA, the SAT, their shoe size, I don't know, that kind of, that's the attribute. So in this case, our information gain will only be looking at the class for calculating entropy, because we're looking at entropy, since we already split it using the left child, right child concept, we don't need to actually look at the class. So given that, does everyone try, do you want to try it again? All right, say again? Yep, why? Yep, so it's we call information gain. And we give it, remember how the first parameter is parent in our technically all of our data. So the original data is just Y. And then we split it into our left child, which is just Y left. Y left. Y left and Y right. Does everyone get that? Yes.
Why are you doing y.reshape reshape 1 negative 1 transposed?
What does that mean?
Don't worry about that. That's just changing the dimensions of the data. So instead of the data being like long, we want it to be taller, or vice versa.
So I meant,
I'm assuming you're talking about 121.
Yeah, like what exactly does reshape do? I know it's like, so it changes the structure of the data points and just rearranges it in a certain format.
Yeah, just you don't have to know exactly, but just understand that it just changes it from long to tall or something. I don't remember which way it goes, but it's just so that we can combine the data to be x comma y.
Oh.
So for instance, if we had our x's might be the first column is GPA, second column is SAT, third column is shoe size, and now we just want to xy. It's just the combination of adding the class or whether it got accepted or rejected to the end. So now the columns become GPA, SAT, shoe size, accepted, rejected. That's just what we're doing on line 21. You don't have to overthink the whole reshape transpose.
The, lines 28 to 30.
28 to 30. So because right now we're using the combination of x and y,
Sure.
you only want to give our information function the class, right? Remember how we only want to be zeros and ones if we give it?
Okay.
And so what this does is it says, all right, now that we have split our data into left and right, now let's just go take out the y again.
Is y what you split it with?
Y is the class, sorry. Y is the class, x's are the attributes. Remember the concept of input versus output.
But now we're putting in.
So so line 22 to 23, that's where we split it up by the feature index right there. That's the index.
What is left and right?
So remember how let me actually go show you what it looked like again. Right here, for this tree, right? We say if we split it by whether they have good GPA or bad GPA, the left would be all the data that has a bad GPA. So all the people that have bad GPA, let's funnel their data into that left side. If they have good GPA, let's break up the data so everyone with good GPA goes to the right side.
Are you feeding those two things class information as well?
Yeah, because once we get to that good SAT, we then have to call it again. We still need to know the class information.
Class is good SAT or is it rejected?
Classes, acceptance, admitted, rejected, that kind of thing. Attribute. So the concept of input, output. The output is the class. Output is our leaves, which is the accepted or rejected. Our attributes are X's. This is how we split up our data, is all of the GPA, SAT, extracurricular, shoe size, etc.
So let's say we use good GPA. Why would be?
So if X currently is all of this. This whole thing right here, this is X, this is Y. Currently, you could pick to split it on just the GPA, in which case it would still be this, right? So we split into left and right with respect to a certain X. We're running a bit out of time, but once we calculate information gain, we just check to see, hey, is this our highest or maximum information gain? If so, let's save all this information to use later. And we return that as this is just finding that best split. Let's run that. All right, let's get into actually building, or let's test our best split method. So if you look here, I created a array, 100 by 5 array. So this is our attributes, is 5 columns, 100 rows. And this is just random values. And then our Y, or the classes for this, is essentially if the X, if the second attribute at X, so whatever that middle attribute is, if it's greater than 60, it is going to be a 1. If it's less than 60, it's going to be a 0. And notice I just added in some randomness into there, so it's not a perfect split. So therefore, when we run our best split, hopefully it should notice that, hey, we should probably split it at, again, feature index 2 with a threshold something around 60. It's not going to be exactly 60 just because I added that extra randomness to it. Do people understand this? Can I get a thumbs up, middle, down about why I should be splitting at 60 or how this test works? All right. Hopefully I got most everyone out. All right, let's go on to actually start building our decision tree. So the decision tree, we're going to have a concept of a node. Everyone knows the concept of nodes in a tree. Yeah. So a node contains the feature. So this is at what index of X are we actually looking at? So are we looking at GPA, SAT, etc.? And the threshold is their GPA have to be greater than 4.0, 3.0, etc. Data left is just the node. It's the left child node. Data right, child node on the right. Gain and value. Gain is the information gain. Value. So if this is a leaf instead of a regular node, value would be 1 or 0. Everyone got that? Hopefully, yeah. And then the get display, don't worry about that. That's just for displaying it. All right. So let's actually build it. So decision trees. So our decision tree method, or the way we'll actually be building it, is we want to set a max depth or minimum sample split. Let's just worry about max depth for now. So technically, we could just keep splitting our data until we have however many nodes there are unique data pieces, right? Technically, we could do that, but that takes way too long and you're overtraining way too much. So we'll set a max depth or the maximum size of our tree. So right now, I have the max depth as a default set to 5. That's pretty big. Don't forget, the higher we put our max depth, the longer it takes. And it takes exponentially longer the higher we put max depth. All right, so now we can call build. So what does build do is we start off by taking in our X and our Y. And this will repeatedly split our data until either we've hit the max depth or that minimum sample split that I didn't cover yet. So the first part is we want to get the best split. If anyone sees a pattern in what we're filling in the blank, you go try to guess this. So does anyone want to take a guess for how do we find the best split?
All best split.
Yep, exactly. We call best split. And what should we give it as our parameters? There's really not that many options to give it. X and Y, yes, exactly. So we want to give our best split X and Y. And this is a recursive, what did I do? This is a recursive function, so we call best split. It splits it, so if it's, we have our left and our right child, let's see here, and we want to return the node for that. And then eventually, I think we call build again somewhere in here. Yeah, we call left build and right build. So we build the child, both child's left and right child. We do it recursively. And then eventually we return the current node. And if it's a leaf node, so that means if we've hit the max depth or the min sample split, which we're not covering, we just return the value. And the leaf's value is just going to be the most common class. So for instance, if we have 7 zeros and 3 ones, what is our value going to be? 7 zeros and 3 ones. What's going to be our value if it's a leaf? Yes, zeros, because there's more zeros than ones, right? Pretty simple there. So a leaf is just going to be whatever the data is for the most common class of that data. Did I see a question?
No.
Okay, never mind. I'll keep going. So hopefully that makes sense and everyone was able to fill out that best split right here. It's pretty simple. Yeah. I don't know. I look capitalized in my X's. It's just a common trend. It's really weird. I don't really get it, but X's are capitalized as Y's are lowercase.
Because X usually represents a matrix, Y usually represents a small vector. That's all.
Sure. He knows more than me. So we'll go with that. All right. So now we can actually go to predicting it. So this is a quick and easy function, which now that we have our tree built, given a piece of data, how can we get to the leaf? So I'm assuming everyone's done tree traversals before. This is pretty simple to a regular tree traversal. We first check, hey, is it a leaf node? And we can do that by seeing if tree.value is either a 0 or 1. So if it's not 1, then we just return whatever that leaf value is. Now we can get now if we know it's not a leaf, we can actually get the value to compare to the threshold. So that is called our feature value, which is just the value of X at whatever feature that we're looking at. And then we compare it to the threshold. So if it's less than or equal to threshold, we return just the recursive function. If it's greater than threshold, we return the recursive function, but on the right child. That's pretty straightforward, check if it's a leaf. If it's a leaf, return the leaf. If it's not a leaf, recursively call it whether or not it's less than or greater than the threshold. Okay, a thumbs up if that makes sense. Nice. And then predict batch, it takes in a array of inputs instead of just one. It's just, yeah.
How do you get tree dot feature? Again, I'm a little confused how it's finding that feature.
So remember how we create our own node? We at some point in the code, which I kind of skipped over, we save feature.
Okay.
All right. So everyone should have all that run, so we can actually try testing our data. This might take a minute, but let's go and collect our data. So for now, we have by default the German data set. German data set that is related to whether or not you have good credit or bad credit. So think like the bank, how much money you have stored, how long have you been with the bank, trying to predict whether or not you have good or bad credit. If you want to look at all the data sets, again, that's at the top. You have the adult data set, the bank data set, Compass, and German data sets. So we collect it into X, Y, attribute names and class names. That's just for printing. And then we have, we want to split up our data into the train and testing. That's just so we can get the evaluation. So see how accurate was our data, or how accurate is our model actually. So let's run it. This might take a sec to fetch all the data. Once it's fetched, we can then run the second part. So one, we want to create our decision tree class, and then we want to build it given the training, the training values, the X and Y training. So let's build it, and this will do all that training that we talked about before, which calculating the best split at every single node, just recursively calling that until we hit the max. Why was that so fast? Weird. When I tested last night, it was like a minute. Oh, well. Well, anyways, we got, using this, we were able to train our tree and then use our predict batch to give it the X testing data to get our Y predictions. Again, this is just a very simple accuracy, which is just checking, hey, what's the chance that we got the prediction right compared to the actual result? So you see, with this very basic model, with only a depth of 4, we got our accuracy to be 0.71, so 71% accuracy. If we actually want to see what the tree looks like, we can run the next part, which gets us this nice ASCII visual. So maybe that first node, we have it split at duration. I'll get to that, and then we keep going. Yes, question.
Split duration and residence if all the options are good for it, and then for
So that's a good thing that you point out. So how come all of it turns out to be good credit? Oh, right here. This is what we're talking about.
Yeah.
So again, it doesn't really know what the end leaf is going to be. It's just trying to decrease the amount of entry, right? And so maybe even though it kept trying to split it up, 90% of the data was still good credit. So all this is doing is it's trying to break the data up as best as it can. Maybe it can't do it well, which clearly it doesn't do it well, no matter what, the good credit dominance class.
Yeah.
So it just means there's no good way of doing it. Usually this has pretty much it's here. If you want, we can create a smart method that automatically identifies to give up. Right?
I'm just wondering why I wouldn't just say, oh, I can't split it. Like,
Yeah, so
there's no give up, I guess.
Technically there is. So you say like at some point, remember I have the minimum sample split? That we might, I think that's where we can change it to be a bigger number to say, hey, if we're splitting the data up into 2 and 20, just give up there, say that's good enough, right? And so I think if you want to play around with that, you can. That may or may not fix the issue. But so now if you don't have, we're already past time, but if you want, you could play around with different data sets. If you want to know what the data sets are, I have them above. So just instead of running a German, you can run adult, which is the US Census data set for. No, there is no college. I can make one up. No, I don't have a college data set. Unfortunately, that is a protected data set for probably pretty good reasons.
Unfortunately.
That would be a useful.
I mean, technically, they give us some amount of data. Hey, if someone wants to scrape the world acceptance grants based on whatever exists, that would be fun to do. And we could try to implement that into next week's lesson. But yeah, thank you everyone for coming. If you have any questions, I'll be here for a little bit. I guess I do have a meeting to go after that. No, you two do, so you guys better be running your ass. But yeah.